Yeah, so chapter 1 is trying to just jumpstart you through 106 and even do it at a little more sophisticated level than what we did. And so this is part of the style of the book, is that not everything's going to be spoon-fed to you. And a lot of the content is in the problems. And the problems are like critical thinking exercises, like they're puzzles. But once you figure them out, then you should be confident. Like, because that's kind of like, that's a weird thing about logic. It's persuasive. Yeah. Once you understand it. But it's persuasive in a way that's different from rhetoric, right? Like a con man, like a confidence man, like Trump, he can get people to feel persuaded by what he says, even when there's very little content to what he's saying. You know, that's rhetoric. He's a very good rhetorician. Logic is persuasive in a different way. But there is a kind of feeling to it. Yeah, you do kind of.
Oh, I know when I'm discomfortable. That's number 7. Number 20.
So number 7 was a problem that threw you.
It didn't throw me. It's just that, well, I look at it and I know that for each item, you have to noodle on it for a while.
Right.
So like I made my, like G and H, I'm okay with now. The ones I really am not comfortable with is when I say something follows. If a sentence follows or doesn't follow from another. This gets to like the problem of number 20.
Right.
Right? It's there's these words that I'm sure they have logical meaning, but I don't know what the symbol looks like.
Okay, so, and that's one thing that Jeffrey is doing. Is just using terminology, and you're going to gather the meaning from the use of the terminology. And so follow here in this context means logical implication. In the last lecture I did is the turnstile.
The therefore, the so.
The therefore. Logical implication. So he uses implication in problem 20. Is that the word he's using?
It says implies.
Implies. So implies, but logically, you can say logically implies, and that means we're operating at the level of valid inference.
That's the colon in 106.
There, that's right. So the colon, the therefore.
That's what I took it to mean, but there was no way for me to feel comfortable that I read it right. I had to just have faith and try to use it that way for a while and see if I have success.
Yeah. So, and we could say logically follows.
Yeah. Logically implies.
So if you can throw in logically and it still makes sense, and that sort of indicates that we're operating at this level of logical entailment, valid inference. If that makes sense, then that's probably right.
Because he starts using that more in chapter 2 with Moriarty, where they start asking questions. If this, and this, and does it follow?
Right. So yeah.
So I started just recently seeing that word more.
And in chapter 2 now, then it's a little more natural too. And because of the context, you see that it is an argument, and you're trying to prove whether it's valid or invalid. Yeah. That clues you into that logical entailment sort of level.
What these words must mean.
Right. And so that's what I'm thinking next time through is what I might do is I might have students be working on chapter 2 and chapter 1 simultaneously.
There was one, for instance.
Because that seems to help a lot.
And also, you can tell I'm not the biggest fan of the book, but like there's a problem in chapter 2, and it's asking you to check the consistency of a set of statements. There's no conclusion using the tree method, but it's not until 4 or 5 or 6 questions later where he says you can check the consistency using the tree test. You have to apply the tree to the undenied set of statements, and if et cetera, et cetera. And so, well, thanks for telling me, buddy, but you asked me a question about it.
I think he does say it in the chapter.
I looked.
I think he does say it, because I read it
I don't know,
over the weekend, or maybe on Thursday or something. So it's kind of fresh in my mind. I think he did say that.
But then why would he have a question where he explains explains it again? Anyway,
I don't know.
So so
sometimes you have to say things more than once. That's what you find as a teacher.
Okay, you have five touches,
and you see patterns. It's like, why do people get confused? But I don't know. So
yeah,
and that's what I like about like my online text. Like, as you were running into problems, I could fix them before everybody else got them.
That's right. So like here, like E, if a set of sentences is consistent, each member must be. See, that blows my mind, because how can an individual member be quote unquote consistent? Because consistency is all of the statements must be true.
He does. I think that's in chapter 1 earlier on. He does talk about the consistency of a single statement.
Which would be then at some point, under some interpretation, it's true. That's all I can imagine it would be.
So it's not logically self-contradictory. It's not self-contradictory. So because we did tautological, contingent,
negated tautology,
and contradictory, right?
Yes.
So he's saying a contradictory statement is a inconsistent statement. He just collapses that into consistency.
Okay.
And he's very focused on consistency, because the tree method is really a test of consistency.
Yeah.
So he wants to get everything captured by the notion of consistency as much as possible, because that's what the truth tree does, is it tests for consistency.
Because it related is in the first page, he says, a valid argument is one whose conclusion is true in every case in which all premises are true. I agree that statement is sound, but it's incomplete. That is not the complete definition of valid.
What page are you on?
Page 1.
What does it say?
A valid argument is one whose conclusion is true in every case in which all its premises are true.
That is a complete definition.
It is not complete.
What?
Trivially valid is also valid, and none of it's inconsistent. It has inconsistent statements. There's never a case where all the statements are true, and yet that particular scenario is considered valid. But we call it trivially valid.
But he says in every case where the conclusion is true,
yes,
the premises are also true. Is that what he's saying? Like what is?
Yes, a valid argument is one whose conclusion is true in every case in which all premises are true. If you have, so then I added then, if you have,
well, that way scenario that was different than what I thought it said.
Where no premises are true, the statement is still valid.
Okay, so yeah, so
it's incomplete.
Okay,
it's not the whole truth.
No, I think you're kind of inverting the terminology here. Let's just do this. So he says, whoops,
And he has an example of what I'm talking about.
I don't want that.
One, I think it's in 1.14. That's, yeah, because he shows an.
Okay, so this is a good, this is a fundamental issue. So let's talk about this first. So
I'm not saying he's wrong. He's just not the whole truth.
who's going to, in every case in which, it's not true. Okay. And so let's look at modus ponens again. Okay, so P only if Q, P Q. So and then I'm going to use this turnstile. Okay, that indicates the therefore, and that's going to be significant later on as we get into problem 20. And of course we can write that in the notation of 106. That's easier to type. So we could have P only if Q, P therefore Q. Okay. And we could do a truth table. And so
You're stuck on these truth tables.
And so we can do this, and this is going to be, whoops. Should have known. True, false, true, false. And so our significant rows. Okay, so a valid argument is one whose conclusion is true in every case in which all its premises are true. Okay, so we look for all the cases in which all the premises are true. Okay, so we get this, and that's it. And the conclusion is true. So, and I use a percent sign like a check mark. Those of you listening at home. So like when I do truth trees, you'll see that I use percent signs for check marks. Okay. Let's see. So you're okay with this situation. All right. So a valid argument is one whose conclusion is true in every case in which all of its premises are true. But you're concerned about something where we have like the principle of explosion at work. If we have something like P, we have Q and not Q, therefore R. So this is conjunction, this is negation. And in the alternatively, this could be P, Q, Q, wedge, Q. So that's the same thing. Okay. And we could do a truth table for this. So that. And so we could do, what the heck? Been getting some weird behavior in Microsoft Word recently. It's a new version.
When I use circles, triangles, and squares,
I gave up on that.
it goes wacky.
I did problem 19, and then I was doing problem 20 with all those, but it just became so burdensome.
I think some of them are like meant for reading right to left languages, because as you start moving your cursor, it goes the other direction. It's weird. Eventually, I got it tamed, but well.
Oh, we need R here. Sorry.
Yes, we had the 3 references.
Actually,
No, yeah.
I want to do this.
Yep.
Oh, but I can't do that because I'm not using your Notepad Plus. Is that what it's called?
Yeah, you like that one, huh?
So let's clean this up. All right. So
Yeah, I love that.
I'm going to do true, false, 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 false. Maybe shrink this down a little bit. Okay. And so this is a good thing to be thinking about as we get into these more difficult problems too, is that there are weird things about logic, like this, what I call the principle of explosion here. And what you call trivially valid.
Yeah, trivially. Yeah.
Trivially.
How about vacuously valid? I like that.
Vacuously. That's
Easier
easier to say.
But I don't just, I think it's in the book too. Trivially.
That's right.
More syllables than
Trivially
valid.
So we look for all the cases in which the premises are all true.
You got to fix those ones though.
Where?
Those first 4. That's TT.
Oh, these are T's.
Yeah.
Whoops. T's. All right. And so we notice that the second premise is contradictory, self-contradictory, or in Jeffrey's terminology, it's inconsistent.
Okay.
Right? So the second premise here is inconsistent. This is the way that Jeffrey uses that. A single statement can be inconsistent, just like a set of statements. Okay. And we look for all the rows, where all the premises are true, and there's no row, there's no case. And you're saying that contradicts his definition?
I'm saying his definition doesn't apply.
It does. There's no case in which all of the premises are true.
Yes.
So it doesn't matter whether
It doesn't mean it's valid.
It does.
No, this is just like when Holmes doesn't bungle, it doesn't mean for sure Moriarty gets caught. It just means that he for sure didn't get away. See, this is...
But that would be, okay. So now we know the problem. Okay, so we have a vacuously valid argument.
Yes.
Because one of the premises is inconsistent or self-contradictory. And so let's do this. Let's say let's use different letters. Let's say A equal the conclusion is true the conclusion is true. And then let's let B equal let's say it is true in this case. And let's let B equal the premises are all true in this case. All right. And so it seems that you're interpreting the definition as A only if B.
No, I'm the opposite.
Okay, so good. So that's not the right definition.
This is like saying the lights will be on if the light switch is flipped up. There is no light switch. And then so what he's saying is, well, then the light is on.
So the definition of validity, as Jeffrey has it above, is B only if A.
Okay.
That's what you're saying, right? It's not the other way around. Or is your word going the other way around?
No, I don't think so.
Okay.
The premises are all true in this case, only if the conclusion is true in this case.
Mm-hmm. So,
right. And so when B is false, we cannot make a statement as to for sure what A is.
But it doesn't matter.
Well, it does because he says it is valid. He says it's definitely valid in 1.14. When you have an inconsistent set of statements,
Mm-hmm.
meaning you're in a scenario where you have no truths in the premises, he's saying that is a valid statement.
Right. And
so this cannot conclude that not B means
this is a valid argument. And so this is a valid argument. I mean, this is just the way that formal logic works out. I mean, it's obviously there's something fishy going on here, right? And that just gets to the problem. This is not a sound argument. So this is a very important circumstance in which soundness is the supreme concept. Because it's not just that the second premise happens to be false, like when we were talking about whales and tortoises and all that. It logically is false. Right? It's absolutely false, and so this argument is not sound, even at the level of logic. Right? We don't have to look at the world. We can know that it's unsound a priori.
Yes, I agree.
Before all experience. Right? Have you guys talked about a priori or a posteriori yet?
In 140,
it's starting
kind
to come up.
It's sprinkled in, like Descartes uses it and Spinoza uses it.
Right.
We don't really dive into that.
But this is very important. It's also important to Hume. Oh, did you get a chance to read Hume over the break?
I'm over halfway through all of it. Some of those things you sent are like really long.
Yeah.
So I'm about halfway through them. No, and I'm willing to grant this to be a valid statement. My problem, a valid argument even. And my problem is that the definition for validity is incomplete.
But it captures this case. So you have to find a counterexample, or it doesn't work.
Not B.
Right. So we have not B here.
And so what does that say about A then? Can I conclude A?
Okay, so this is the issue that we were talking about before we got started. The difference between material implication and logical implication.
Okay.
These are the two different levels. So logical implication does not behave the same way as material implication. So material implication is the right arrow, and logical implication is the turnstile.
Okay.
This is also known as material consequence, but we can call it material implication. But we need to distinguish that from logical implication. And they don't behave the same way.
Okay.
They almost behave the same way. So that's what's confusing. But material implication has nothing to do with validity. And logical implication has everything to do with validity. And the definition is B only if A. So
it's not, the complete statement wouldn't be B only if A, comma, negated B, therefore negated A? Can we make
no, that's not what
be an argument? Can we make it an argument, or it has to be a statement?
But that argument is not valid.
I know. But
that's not what this is saying. It's not an argument. It's just a pure statement.
And it can't be an argument.
Right. So, and we can't quite symbolize this yet until we get to quantification. But once we get to quantification, we can symbolize the definition
of validity.
Okay. In a way that will be tight. But this is at the heart of it.
And then we can answer 20.
But we need to get it before then. So there's no argument here. It's just a single statement.
Right. Okay.
When this is true, the argument is valid. When this is false, the argument is not valid. This statement is true for this argument up above.
Only because A is always false.
Only because B is always false.
Yeah.
So when the antecedent is false,
doesn't matter what we don't care about A.
Conditional statement is true.
Yeah.
It doesn't matter whether A is true.
Yeah.
So this is vacuously valid, this argument up above, but it's unsound. And so you cannot, the argument does not imply the conclusion from the premises because it's unsound.
Right. So we cannot conclude.
But it is valid.
But that's the conclusion. How can you conclude the conclusion? The conclusion is A. A is
No.
indeterminate.
No, the validity is about the entire argument. It's not about the conclusion. The validity is about the entire argument. The relationship between the premises and the conclusion in terms of validity. And this is just what the definition of validity is. It doesn't guarantee you that the conclusion is true. That's the whole point about soundness.
But there's no relationship between the premises and the conclusion in this case.
Right.
So you can't then say with the definition given, you can't say it is valid. You can't say it's not valid or invalid.
You can say that it's valid. Valid's one thing, soundness is another. And a sound argument has to be valid in this technical way that we're discussing. And then it also has to have premises which are in fact true. And premise number 2 here it's not possible for it to be true. So this argument can never be sound. It's unsound a priori before I go check.
No, I'm not on soundness. I'm just suggesting that the definition for validity should be all arguments are valid unless any case which has all of its premises true and the conclusion false. That's how it should be stated.
But you're just arguing. But it's just like a rewording of the thing is if it's logically the same, it doesn't matter how we word it.
It's different. They're not the same.
Then how would it be symbolized different?
Well, it starts out with that the default condition is the argument is valid, and now you have to do the test to see if you can make it invalid.
So, but the way that Jeffrey all I'm saying is the way that Jeffrey states the definition of validity, that's just he didn't make that up.
I know. It's been wrong all along.
but this is just what it means. It's just a technical definition.
But this is logic.
It's like you could define something different. That's fine. But you can't just change the definition of a technical concept that's already in motion.
So, like, if we follow,
you could call it, schmelziness or something.
No. I'm not attempting that. So let's imagine we have a trinary state, right? I know an argument is valid. Well, I don't know if I know. An argument can be valid, it can be invalid, or it could be unknown.
But that's a different kind of logic. So
I'm just trying to use it as a device
in traditional
to describe what I'm.
I know, but it doesn't even get off the ground because in traditional logic, we have bivalence. So a statement is either true or false. That means that an argument
is either valid or invalid.
There's no third alternative. There's no middle. Like we call this excluded middle.
And the default we grant them is that they are all valid.
Well, okay, so maybe this is where the implication is. One thing about definitions when we get in logic, and this is something that's not made clear, is we say an argument is valid if, like we might, if B like we might give the definition like this, and that'd be like, but really what we mean is if and only if.
And that's, no, that's not what this means. That's not what we're, That's how but that's not what it says.
I know, but that's just the way that definitions work. I know.
No, but
That's just a convention of English.
But it's not, because you're saying if and only if, meaning that you must have a premise is true condition in the if and only if.
This is all
arguing this is
conditional.
what it should be. Yes.
This is all conditional. So this is hypothetical. It doesn't say that B is true or A is true. It says nothing about the truth values of A and B.
Well, but we define B as the premises are all true in this case, and A as the conclusion is true in this case.
Right.
I'm suggesting that's the definition. Well, no. Let's see.
So this if and only if thing, I remember getting hung up on that. But this is really what we mean. If it fulfills this, it's valid, and if it's valid, it has to fulfill this.
But the one above is valid, it doesn't fulfill that.
It does.
It's vacuously valid. It has no,
I know, but that's okay.
but it's not if and only if okay.
It is.
So then what is an argument? So let's say
This argument is valid,
why?
and this is true. So this is true for this argument. So this argument up here.
But B says the premises are all true in this case. Where are the premises all true?
Okay, so maybe we need to, if we do the only if A, right? And it's important for those of us listening at home, watching at home, you have to at some point struggle with material implication and its weirdness. This is just something that you have to go through. This is, and then we have to also struggle through the fact that material implication is not logical implication, and that validity is not soundness. These are all distinct concepts. And what we really want is not just valid arguments in scientific discovery or philosophical discovery. We don't want just arguments that are valid. We want arguments that are sound. Right? This is true. This is false. This is true. So this statement is true except for when we have this situation. When B is true and A is false. Right? But other than that, it's true. Correct? Mm-hmm. Yeah. So when we look up here, the conclusion is true. We see that we have case 1, case 3, etc. So we have here these top 2 cases, and the statement is true in those cases, regardless of whether B is true. And if the conclusion is false and the premises are not all true, if it's false that all the premises are true, then the conditional statement is again true. So we're just saying that this case doesn't, the false true case here, that the premises are true and the conclusion is false, that just doesn't happen. And that doesn't happen. That doesn't happen anywhere here. So there's no instance when all the premises are true and the conclusion is false. And that's what that conditional statement says. Right?
I don't think so.
But that is what it says. I mean, that's what the truth table tells us. That's what all this means.
Or we have it symbolized wrong.
But I'm just saying that this is just the way it is. Like, this is, like, validity is a technical concept. Like, within logic. It's like force in Newtonian mechanics. It's defined as mass time acceleration. Some people may not like calling that force. Okay, then call it something, call it Fred. We don't care. You can call validity Fred.
No, but my argument is about
in this book, when we talk about validity, this is what we're talking about. In this context, And it leads to unfortunate occurrences like this. However, we have the concept of soundness that explains that this is an unsound argument. But I think what you got yourself into is thinking about logical implication as somehow tied into the logic of material implication. And that's what the problem with number 20. Because that is, and now you're projecting back onto material implication the issues that you're having with logical implication. So let's move on. We can come back. We can circle back to this. But this is the proper definition. And when we say an argument is valid if, we really mean if and only if. But in English, we just say if. We don't say if and only if. We mean if and only if. So, what does this do for us? Okay, so let's look at problem. So 19 and 20 then are the big issues. So maybe we should wait to see if Arthur shows up, because he's supposed to present problem 19.
Oh, okay.
So we'll see if he does that. So let's hold off on actually talking about problem 19. But we can talk about, so what if we do an argument that's like this? Let's do, let's just start fresh now. Let's say, this is a valid argument, right? Is vacuously valid. Because the single premise is contradictory or inconsistent within itself. So we have both A and not A. So the sun will come up tomorrow and it will not come up tomorrow. Therefore, I'm going to win the lottery. And this is a valid argument. Can I take that to the bank?
Take it.
No, because it's not sound. It's not possible that the sun will come up tomorrow and it won't come up. It's logically impossible. I don't have to wait till tomorrow morning. I know that before the fact, a priori. So that's what a priori means is like at the previous, prior to the event. And the opposite of this, that is a posteriori, which is after the fact. So
Can a sound argument be invalid?
a sound argument cannot be invalid.
But a valid argument can be inconsistent.
It can be unsound.
But it can also be inconsistent, which seems peculiar. Because consistency or not,
the argument
builds
is
up.
But this is where we have to distinguish between.
I'm just saying I understand that is the truth and it's the case. I'm just surprised that they decided from a definition point of view to that inconsistent statements would be considered valid arguments.
But an inconsistent statement is not an argument.
But the input to an argument being inconsistent?
Yes.
I'm just surprised from a definition point of view from way back when that they would grant validity to an argument comprised of inconsistent premises.
And so this was a big, I mean, it wasn't really controversial, but it is something that is discussed quite a bit, especially in medieval logic, because it just doesn't seem right, right? But they discussed it enough in the medieval amongst the medieval schoolmen that since then it's been a settled issue. Because they took Aristotle as the philosopher, and Aristotle's logic leads to this circumstance. So, they treated Aristotle, almost like the Bible. Like it was, it descended from heaven. So,
Okay.
So they swallowed it, and then the concept of soundness does fix it. And soundness is an issue apart from these sort of circumstances. If you just have the facts wrong. And so this is called the principle of explosion. It explodes an argument. And they had a Latin phrase, which I can't remember, but it means from contradiction, anything. Right?
It's kind of like the or. You can tag the or onto the end of anything.
Yeah, addition, yes. So from contradiction, you can derive anything. Yeah. But that doesn't mean that your conclusion is true, because your logical implication that you're involved in is unsound. Okay. But notice here we have a single proposition implying another, and that's in problems 19 and 20. It's all sort of reduced down to statement A logically implies statement B, right? Or circle implies triangle, right?
20 has square
and square,
and then it has multiple. They get used in multiple ways. Turning it on and off.
Sure, right.
You're still saying that's still just one statement, one proposition, and one conclusion?
Yeah.
Oh.
Yeah, so the circle, the triangle, and the square are just, each of those is a single statement.
Are there commas between those statements?
Commas?
Or is it like A and not A is different than A, comma, not A.
Right.
So when we're talking, I can't see if there's a comma or not, or if there's a conjunction when you're saying Like I'm imagining commas.
You're imagining commas.
20, I'm imagining like 5 commas,
Okay, so we could do
6
something.
premises and 1 conclusion.
We could do something like this. Let C equal a. So then our first argument here, our first argument here would be logically equivalent to C, dash B,
Yeah,
right?
yeah.
And we could have a different argument. We could have something like, we could do A, neg A, right? And this kind of gets at the issue between the difference between logical implication and material implication. So, this is again, is a valid argument, right? Because there's not going to be any case in which A is both true and false. It has to be one or the other, excluded middle. And so this is a valid argument. And then we could say, we could say let D, or we already have that. We could, what was I thinking here? Because you sent me that that proof that was kind of like problem 19.
Yeah.
So the theorem of problem 19 is implication and conditional. So Jeffrey is really introducing this whole problem. How you compare material implication to logical implication. So this is what problem 19 is all about. So one sentence logically implies another if the argument from the former to the latter is valid. Show that a sentence circle implies a sentence triangle if and only if the conditional circle only if triangle is a tautology. So let's just assume that 19 is true. Arthur is going to prove it for us, right? But if we take that as a theorem, then we can say, like up here, we can say, break here. Oops. Here we can say, then oops. We can say C only if B is a by problem. Because what does C only if B rule out? It rules out the possibility, the case, that C is true and B is false. It lets all other cases be. Right? All other cases are fine. If C is false, it doesn't matter whether B is true or not. And we can, in the way that proof that you sent me, you could say then C B is tautology. This also works. You could, because C is just the conjunction of the two premises. So you can, this is more general, like for arguments with multiple premises, you can just conjoin all the premises with conjunction and make it into one big statement. And it all works out, not exactly the same, but there's a connection there.
But logically equivalent.
That's what I don't want to go so far to say that they're logically equivalent.
Okay.
So for example, if we go back up here, so if we go back up here and we have this argument, right, which we know is valid, as we discussed, vacuously so. We can say, whoops. Then, do. We could say this is valid. And we could say that But saying that this conditional is a tautology is not the same thing as saying that the argument is valid. They mean different things.
Yeah.
This theorem just proves that the validity logically implies the tautology. And it also says actually that the tautology logically implies the validity. But the conditional being tautological is not the same thing as the argument being valid. And we can't, for example, we can't put like a symbol that says logically equivalent between these two, between the argument and the statement. And in fact, logical equivalence only applies to statements, and an argument is not a statement, right? So to say, symbolically it would be an error of syntax, but conceptually there's also a problem of saying that these are logically equivalent.
Oh, I meant like a comma, not a, and a conjunction, not a.
Yeah, and again, those are not logically equivalent because a set of statements is not a single statement. Only a single statement can be logically equivalent to another single statement. And so this gets at the difference between this material level versus this, for lack of a better word, logical level.
Mm-hmm.
Or, just because of the difference between material implication and logical implication. So we can say that this is true, but we're not going to say that sets of statements is equivalent to a single statement. That's not true. And so we just have to say what we can say, and what can't be said, we just pass over in silence, as Wittgenstein said.
And the fact that it's a tautology is only because the antecedent is always false. It's not because it's valid.
Well,
it's only vacuously valid.
No, according to the theorem from problem 19, it is because of the validity.
Oh, so even regularly valid is also a tautology.
Yes.
Because the consequent is true in every case where the antecedent is true,
mm-hmm.
and never false consequent with a true antecedent, which is the only condition in which it would not be a tautology.
Right. So the only case in which that would show, that would be a counterexample for its tautologicalness, is the same case that would show the argument to be invalid. So the counterexample for tautologicity is the counterexample for the invalidity. So they pick out the same counterexample.
I feel
or they eliminate the only possible counterexample.
Yeah.
You feel like what?
I feel convinced.
Okay.
Not because Trump was talking in my ear.
So
okay, that's the crux of 19.
Yes, that's
right.
what 19 is all about. That's what's being proved, right?
And so in theory now, if I take that to the next step.
So that's what you need to know in order to really do problem 20.
Okay. And operate on the logic level versus the material level.
Right. And so that comes into play. I think here, this is a good example again to look at this, because if we go back up to the truth table, now if we think about the premise, think of collapsing this down. If we collapse that down into a single statement, P and Q and not Q.
You can combine them with a conjunction if you want.
Right. And then there wouldn't be any T's at all in any of the cases amongst the premises. It would just be all F's all the way down.
Yeah.
And then it is kind of closer to the material implication sort of structure. But we
can't apply the material implication on a set of statements. I can only apply it like with logical equivalence. I can only apply it sentence by sentence.
Right. So you can't do this. Like that's a big part of 19 and 20 is what is being implied, not logically, but just implicit instead of explicit, is that through working through the troubles of 19 and 20, part of what you're learning is that you can't say that a set of statements what did I have? P and what did P and R? This is syntactically wrong. Like you just can't use material implication in this circumstance.
Unless I conjoin the two statements.
Right. And when I put curly braces around that, that just means it's a set, right? Like a set of numbers. Like if you said curly braces 1, 2, and 4, that's a set of numbers. This is a set of statements, and the order doesn't matter. It's an unordered set. But you can say, that we are saying, oops. We can say that.
And our job is to show that that is valid. And we can do that by conjoining statements and demonstrating that those conjoined statements materially implicated to R is a tautology.
Right. And we don't even need to worry about multiple statements. We can just reduce it down to, we can just say for any A, and any B, if A logically implies B, or A logically implies B, if and only if A. So that's really the theorem of problem 19. For any A and B. That's why, he introduces the circles and triangles so it's kind of implicitly introducing quantification without getting into all that rigmarole that doesn't come up until chapter 3 or chapter 4, right? Maybe chapter 4.
Yeah.
So you want to think of circle as any statement, triangle as any statement.
But when you attach conditions, then it's no longer A is any statement. It's any statement, but that also meets these other conditions.
That's right.
So
that's especially in 20, that becomes very important.
Yeah.
Well, yeah.
Because it's explicitly saying it, and also you can't, the reverse is not true.
Right. So this is just problem 19. This is the theorem of
Arthur can do 20. I'll do that.
Well, that's why I didn't give it to Arthur. Because we'll see if he gets 19. I mean, 19's tough. Right? And 20's.
Well, if you think 19's tough, wait till you get to 20.
Yeah, right. So these are the last problems in the list. So,
yes.
Thanks. Not everybody's going to get there, right? These problems weren't in edition 3 of the textbook.
Should have started a couple of years ago.
So these are problems that Jeffrey added over the years between, since the publication of the 3rd edition.
This little piece of paper.
Yeah, those slips of paper. But then But then look at all the mileage that we've gotten out of these problems, because now we're talking
12
about, and we now we're really understanding these different levels of logical implication versus material implication. And there is a connection, right? That's what problem 19 gives you, the connection. But they're different concepts. That's very important, especially for problem 20. Okay. Because you were at points conflating material implication with logical implication.
I don't know if conflating is the right word. I was trying to use our regular tools in, I'll say, logically equivalent manners.
Mm-hmm.
You know, it's similar to the way in which you demonstrated that you can conjoin all the premises into a single statement, and then you can apply material implication to the conclusion, and that's perfectly fine, but you're looking for tautology now.
Right.
Because if you find tautology, then you know that the original statement was valid.
Right.
Even if you don't have any other way to know it's valid, but you have this tautology test, then you can conclude it's valid.
That's right.
And so it wasn't a conflation. I knew I was doing something, but what I was getting at was kind of like that, where I was trying to use, because if I can get it into a form that uses regular tools of logic, then I get to use all my rules of inference and my equivalence, and
right. So
I have my toolbox available now.
Right. So, but what Jeffrey is sort of forcing on us too, and that's kind of what chapter 1 is about, is he wants you to let go of truth tables. Right. I'm
fine with that. I like the trees.
And even the rules of implication and everything. And he wants you to think in terms of counterexamples. And so one thing about chapter 1 is that it's trying to untrain you from what we did in Philosophy 106. It's showing you the limits of that whole methodology. Right? So chapter 1 is about showing the breakdown of these traditional sort of tools. And he's also assuming like you're not familiar with quantification, right? So he uses the circles and the triangles. So my whole approach to Philosophy 106 is just to set you up for Jeffrey. Right.
So he can knock me down.
Yeah. So he can now tear down what we did, show that it only goes so far, but then he's going to build a whole other system that's rooted in these truth trees, but there's a lot more to it. And then he's going to show where that breaks down. Right. That's what we're getting to at the end of the book, is like, he's going to say, okay, zero level logic. Okay, that breaks down. That's chapter 1. He's just sort of give it a try. See, he's like, it's not going to work out. You're going to be forced to think in terms of counterexamples. And then once you're thinking in terms of counterexamples and consistency of statements, and counterexamples involving consistency of sets of statements, that's what the truth trees are all about. We can get a lot of mileage out of that. But then we push it, and it breaks down. But this is not something that there's an alternative to replace it. This is just where logic, as far as we know, breaks down. So I have this little discussion here, and so maybe we can go through this, and hopefully that'll set you up to solve 20. And this is all very related to what we were just talking about.
Yeah.
So the proposition of 20, and I've replaced the circles and the triangles and the squares with letters. So A, B, and C.
Yeah.
A is circle, B is triangle, C is square. Okay. Because I got tired of
Yeah.
I got tired of this.
Yeah.
Yeah. I got it to look pretty good, but then as I was, working on problem 20 and I was actually throwing stuff out and rewriting it, was like, oh, forget that.
Oh, I just do PQR and then when I'm all done, go back to replace.
Oh yeah. See, that's it. Yeah. So the proposition that we're trying to prove is if a sentence A implies sentence B, and we can use the turnstile to say that, but B does not logically imply A, then there exists a sentence C such that A logically implies C, but C does not logically imply A, C logically implies B, but B does not logically imply C.
Yep.
Okay. So this looks familiar. You got the translation in your head to my symbols.
That's how I originally decided implies means. And then,
good.
But I didn't go to the next, because I didn't have 19. I for sure didn't have 19.
Okay.
Like
So,
now.
and that's the thing. It's like 19 is essential. You can't really do 20 without,
You need to pry things open.
And so,
yeah.
Oh, and notice that I put exists in here. There exists. That's like the language of quantification, which we won't get to until later in the book. But Jeffrey says, then there is a sentence. He doesn't use the word exists because he wants to, he's just kind of implicitly starting to talk about quantification, as it's necessary, because it's really necessary here. But he doesn't want to overburden, conceptually, the problem. You can work through this without worrying about what quantification really comes out to be. So we need to prove that our conditional proposition is a tautology. I must have eliminated. Let's get rid of that. So leveraging problem 19, we need to show that taking A implies B, but B doesn't imply A as premises entails the existence of an appropriate C. Okay. Now, if we assume that A entails B, but that B does not entail A, that means, according to problem 19, that A only if B is a tautology. It's necessarily true, but it may not be true that B only if A.
See, and that was part of I didn't know how to interpret not B, therefore A, because in sort of regular logic interpretation, you would just say, what's the value of B, therefore A, and then flip it because of the negation symbol. But
right.
Not what you do.
Then that's not what we're doing.
But it was certainly one way you could go, but I had no way to know, was that it? Or was it simply, it's unknown?
And that's a good point. So, and that's what,
negation to me is a switch.
Right. So the switch here though is valid versus invalid. The turnstile claims that the logical implication is valid. The negation says, no, it's invalid.
But you said it may not be true. So it doesn't mean that it's invalid. It just means that we don't know if it's valid.
Oh, that's right. That's right. And so
this is my argument. That's why I brought up.
Okay, this is important.
you want to apply the negation symbol right before the turnstile. It seems.
Well, that's what the brackets mean. Look at the dominant operation
Within the brackets.
And that's negated.
But we're not flipping it.
We're flipping it from valid to invalid. So arguments are valid or invalid. Statements are true or false.
Yes. But
so that's what I was just saying, is that the term
may not be true. But that's different than saying,
well,
it's invalid.
This may not be true.
The tautology, it may not be a tautology.
And that's the thing about.
And if it's not a tautology, then, well, that's just another way of saying that the overarching argument is invalid. When you're saying may not be true, so you're saying the overarching argument may not be valid. What it meant.
Yeah, we could actually say, according to 19, that but it may not be true. Because there would be cases where this would be true. Let's see.
And you have a non-tautology.
When I say it may not be true, I just mean
okay, so can there be cases where I have my be only if A is not a tautology? No. If I have cases where be only if A is not a tautology, so sometimes it's true, sometimes it's false,
right?
Then that means
some cases
that the overarching argument it's based on is invalid.
That's right. That's different. That's the if and only if.
Right.
Of problem 19.
Right. And so when you say may not be true, that's different than saying negated B, therefore A. Because if B, therefore A is valid and you negate it, it is invalid. It is invalid. It's not that it may not be valid.
Right. But this statement says that the logical implication is absolutely not valid.
Which means that B only if A cannot be a tautology.
Which it means it's absolutely not a tautology, but it may be true in some cases and false in others, or it may be false in every case.
But if it's false in any case,
that's fine.
Wait, but if B I'm trying to keep my levels separated. If B only if A is not a tautology.
That means it's either contingent or contradictory.
Well, the B only if A, but not the overarching argument.
Arguments are not contingent or tautological.
No. They have this tool we got from 19.
Right.
Where I can basically consolidate an entire argument. I'm sorry, an entire argument
into a conditional statement. I have this, but you can't really make it into a conditional statement. You just know that the conditional statement is tautological if the argument is valid.
But I don't know the other way.
Well, if and only if the argument is valid, then the conditional statement is tautological.
If the statement is tautological, do I know it's valid?
But what you don't know is that if the argument is valid, the conditional statement is, if the argument is invalid, what you don't know is that the conditional statement is false.
Oh, because it depends on which case you look at.
It's case by case.
One case, it could be true. One case, it won't be tautological.
It won't be true in every case.
Yeah.
And I think that was where, you're trying to collapse it too much. It's just that the conditional statement is tautological, which means that it rules out the one case where the antecedent is true and the consequent is false. It eliminates that from the universe of this problem.
If your B only if A is tautological.
Mm-hmm. So
A only if B was.
Yeah, so A only if B is tautological within the universe of this problem.
That's given.
That means the reality of A being true while B is false at the same time
Doesn't exist.
that doesn't exist in this universe.
So when you say your IE, it's not a tautology. Should it be IE, it may not be a tautology? Or for sure?
We know it's not a tautology.
So then...
Because if it were a tautology, then the argument would be valid by problem 19.
So then if we say, but it may not be true that B only if A, meaning that sometimes the value of the material implication is true, sometimes it's false.
It might be always false.
But it can never be always true.
But we know it's not always true.
So we know it's sometimes false. It must be sometimes false.
It must be sometimes false. It's false.
So I could also say, but it is sometimes the case that B only if A is false.
That's right.
Right.
There's at least one case in which B only if A is false.
Right. And that's the takeaway we get from the proposition.
And there's only one case in which B only if A is false.
Oh, he loves that case. That's what hinges his entire methodology is when if you know without question that material implication is false, you now know the left and right inputs.
That's right.
There's no two ways about it.
Right. So when
you try to leverage that as much as you can and get as many miles out of that, because that's your saving.
Right. And so if you're doing material implication, you want to look at true false.
Yeah.
If you're doing conjunction, you want to look at one is false or the other is false.
Yeah.
If you're looking at disjunction, you want to look at the one case where they're both false. Okay. That's how you get to counterexample. Okay. So an argument is either
true or false.
No.
Valid or invalid.
Argument is either valid or invalid. A statement is either
consistent or inconsistent.
That's true, but it's also either true or false. A statement is true or false. An argument is valid or invalid. So this is like an analogy. An argument being valid or invalid is to a statement being true or false. And then you go on to something else. But there's some sort of analogous relationship there, not that they're logically equivalent.
No.
But the concept of validity applies to arguments. It does not apply to statements. The concept of truth applies to statements, and it does not apply to arguments. You cannot say that an argument is true. We can say that it is valid or invalid. In some cases, like when we have the principle of explosion at work, we can say that an argument is unsound, logically unsound. But in most cases, we can only determine unsoundness based on going out into the world and experiencing the world.
What do the people say today?
Yeah.
Because it may be sound today and unsound tomorrow.
And that could be. And that's part of life, because
Black swans and such.
Today I'm wearing this sweater. Tomorrow I may not be wearing this sweater. And so the statement, Rodney is wearing this gray sweater, will be true today and it will be false tomorrow. Right, that's just part of the dynamic nature of reality. And that's my whole discussion in 106 about Parmenides and all that. That's what Parmenides is getting at, is that logic cannot capture the dynamic nature of reality. In order to capture the dynamic nature of reality, you have to think in terms of dialectic. And especially like Hegel's sort of inflection of dialectics.
In the way that single members can be consistent or not. Can they also be, or could we also consider single member statements to be sound and unsound?
No.
Because we use the word true or false in two different ways.
Only an argument can be sound or unsound. The concept of soundness only applies to arguments.
Mm. I wanted to stretch it the way that he stretched consistent.
Yeah, but consistent, a set of statements is consistent. And you can say a single statement is consistent with itself, internally consistent.
But that gets to the whole thing of soundness, right? Is we don't look at the conclusion of an argument to determine soundness. We look at the premises,
right?
Determine if they are in fact true in reality.
Because the whole point of making an argument is to prove something that you cannot directly observe. Right? If we could just observe it, we wouldn't need an argument.
If you trust your sense.
Okay.
No Arthur today, I don't think.
I don't think so.
But we covered quite a bit there for 19.
Yeah, we got to the takeaway, right?
Yeah, we have the tool.
Right. And so
we'll spend another 12 hours on this one, and then I should have it.
Yeah. But this will help quite a bit.
Yes.
So leveraging problem 19, we need to show that taking A implies B, but B doesn't imply A. That entails the existence of some appropriate C that meets all these conditions up above. Right, and there's 4 conditions. And when we assume that A implies B, but B doesn't imply A, then we know that A only if B is a tautology, but B only if A is not a tautology. Okay, so, and here's the takeaway from that. So it can't be that A is true while B is false. That case, eliminated. There's only 4 cases, right, regarding A and B. True, 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 false, false, true, false, false. The true, false case is eliminated. So we have this set of possible cases for A and B.
Mm-hmm.
We can have true, true, false, true, or false, false, but the second case, true, false, is excluded by
Not within the domain.
but it's not within the domain of the constraints of the problem, right? Because we're assuming
Because it's not a proposition. You get,
we're assuming this, and that gives us this. So now we've eliminated one case.
Mhm.
Okay. Now let's consider the criteria for sentence C. First, A allegedly implies C. So we know that,
This is like a supposition.
yeah, so let's suppose that A implies C, because that's what's alleged.
That's what he's asking us to do.
That's what he's asking us to do. So this is not a proof. This is more of an exploration.
Okay.
So this is just kind of sketching out
Okay.
what we need out of C.
Yeah.
And then the most effective way to prove problem 20 is to find a C that works.
There might be more than one,
There definitely is more than one.
but we only are.
I found
all of them.
I think 3.
Isn't that all there could be, or no? No.
No, because you can use any connectives and parentheses and so there's lots of options.
Okay.
You could always just say or blah 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 probably, right? You could do just add something at the end.
Yeah. Or D.
Right.
Okay.
So so first let's assume that A does imply C. That would mean that we have the case TT for A and B. Because if you have A, right, we could put that in here. Then B, if A is true, then B is true because A implies B.
Oh, because that's the only, out of our 3 options, only one of them has A true. If you had chosen A false, then you'd have to also choose B.
Yeah, so if A is true, we know that B is true. Because the only 2 remaining cases have A as false.
Right.
Right. That just means that A only if B is a tautology.
Yeah.
So that's the import of problem 19. Like, you think when is A only if B false? That's excluded.
Oh, you're not, okay, you're, the A, therefore C is, you're just taking the first bit from the question.
That's our assumptions. Right? That's our premises.
Oh, no, A, therefore C. What did I say, B?
Oh, yeah, this comes from here.
Question. You're just taking each of those members.
One by one.
Well, not members, I guess, because they're arguments, but.
They're members of the set of criteria.
Yeah, okay.
They are objects. They're just not.
Okay.
They're just not statements.
They're not statements. Okay.
So let's assume A implies C.
Mm-hmm.
And actually, this is yeah. I don't want to put this. Actually, that's not correct. Just just fill in the gaps.
Right. Well, the C has to be true because it's the only situation that results in a valid A, therefore C. Oh, wait, no, it's the only one where it results in the equivalent material application being a tautology, which would then ensure that A, therefore C is valid.
Yes, that's right. But I want to think about it in terms of cases, because we're trying to, we want a C
That works everywhere.
that works for all the possible cases that are left open by the premises.
Right, because we got 4 that we have to work on.
And we have to make sure that
One
C works that way in all the cases that are left open. And there are 3 cases that are left open.
The second, third, and fourth, or no, it must be those, because we only have 2 of the unknown, 2 of the.
Right. So our premises rule out 1 case, but we're left with 3. Now C has to work appropriately in those 3 cases.
In all 3, or only just one of the 3?
In all 3, because yeah.
Oh, because we don't control those cases. They could pop up
They could
in
pop
our
up.
universe.
Right.
And we want to show that within the universe.
And one thing I noticed in your work so far is that you were eliminating the first case.
Well, it's because of the way I interpreted negated B, therefore A.
Right. And so this is very significant. Actually, this is what I wanted to say. That reminds me, is that you were eliminating this, and then you weren't going to get to an appropriate C. I could see that because you have to have C operate within this PT case. It has to be true in that case.
Yes.
Okay. So that's important. But now we're going to get to the part that you already sort of crunched things down to. So second, allegedly C does not imply A, right? So there's a possible case where C is true while A is false. In other words, C is true only if AB belongs to these 3 cases.
So this is my struggle. It says there's a possible case where, okay, do I have to prove that it for sure is a case, or that it's for sure not a case? It's a possible case. Okay.
Well, that gets to the issue
care?
of validity. If there's a possible case where C is true and A false, that's what it means for it to be invalid. Right? Because you could have a case where C is true and A is true. That doesn't mean it's valid. If there's a case where C is true and A is false, then it's invalid. But just because it's invalid doesn't mean that there is not a case where A is true and C is true. See what I'm saying? And there's an asymmetry, right? It only goes one direction, just like material consequence only goes one direction.
Yeah.
So just because so when we say that this argument is invalid, C implies A. When we say that's invalid, it could be that there's a case where C is true and A is true, but we know there's at least one case where C is true and A is false.
And do we have to eliminate that then? That scenario?
No, because we want to, that's part of the nature of C. You have to have a case.
Embrace it.
Where C is true and A is false. And maybe my symbols here, I don't know if I want to use only if here. I'm kind of stretching the symbols, but what I'm trying to say here is that
You already said it was syntactically, not syntactically correct.
right. Well, this is not saying C
You didn't use.
materially implies this set. It material implies the statement that A and B must belong to this set of conditions. Must be in these cases.
But we already know that's already
Right.
given.
So the point here is that none of the three cases, let me see, is out. So none of the three cases is ruled out. But when we get to the third condition,
Let's ignore it for now. I mean, we have to just kind of move on and come back later for the second.
yeah, and just keep in mind that it doesn't rule out any of these cases.
Okay.
But when we get to the third condition, whenever C is true, B is true. So if C is true, then we know that we're in one of these two cases. So C is true only if we're in case TT or case FT.
Because C is allowed to be true or false.
Yeah.
But sometimes when it's true, then
A and B are
it'll
true.
knock out one of the options for A and B.
Right. It knocks out. This third condition means that it knocks out this. C can't be true when A and B are false. Because notice that B is true in these cases. It's only false if A is false. So whenever C is true, B has to be true.
Yeah.
And that just means we're in these two cases.
I'm okay with those. It's the negated therefores is that I've always had my trouble with.
Okay, so here now,
Yeah.
and number 4 is, it's not the case that B implies C. So there's a possibility that when B is true, a possibility. We got to leave open the possibility that B can be true while C is false. Thus, if B is true, then C can be either true or false.
Mm-hmm.
So when B is true, then this is really the crux of the issue. Okay, so when B is true, C can be either true or false. And that's what you got to in your, you know how you were focusing on that one, those two cases?
Several, but yeah.
You were focusing on the case where B is true, where, what was it? A is true and B is false? I can't remember.
I thought it was.
No, it's false true.
Yeah.
So where A is false and B is true. So you were focusing on this case, and what you discovered is that C could be true or false in that case. In those.
Yeah. So I thought I just picked one. Because I only.
No, you have to leave it open. That's really the crux of the issue, is you have to get a C that could be either true or false when A is false and B is true.
Not a C or a therefore.
What's the question? Sorry.
But is it the C that has to be figured out, the true or the false, or is it when C is put into an argument, the value of the argument?
Well, you want to think about a C that meets all of these criteria. And the difficult part is to find a C that when that is independent. I said in our discussion on Pronto, I said independent of A and B. It's really just independent of A.
Because it doesn't care about the B.
The B is true whether you're in the TT case or the FT case.
Yes.
So B is true in either of these cases. And C is only constrained in those two cases. So we don't have to worry about the FF case. It's agnostic about FF.
Yeah.
Right. Well, it's false, actually. I think we came to that conclusion.
Well, because in the first A,
Yeah.
or C,
So we know that C
out.
is false in the FF case.
He is. They show it. Where does that come out?
Right here in this third. So whenever C is true, B has to be true, and B is only true in these two cases. The FF case means.
So why can't we say so whenever C is false? Why do we have to say whenever C is true?
You could say that. I just don't know what that's going to get you.
Because you're trying to invent TF scenarios in order to
Get a counterexample.
a counterexample.
Right. Yeah, and that might be a more comprehensive way of
Because
solving the problem.
when you're looking at C, therefore B, you can also think of it as C only if B, right? Because we're using the tool from 19.
Yeah, there might be a way of doing that, yes. That's not really what I'm doing here, though.
So then how are we using 19? But where does 19, are you using 19?
I used it up above to whittle us down to this.
Oh. Because it seems
And you might get more leverage.
odd that you would use it there for A only if, A therefore B, but then.
Yeah, so you could go. So you can go through this again and then that means this conditional statement is a tautology, but make sure you say it is a tautology, right?
Yeah.
And when there's invalidity, you say that the conditional statement is not a tautology. That means there's at least one case where the antecedent is true.
It must not be a tautology.
Right. But there is a takeaway here that's important. So, so this fourth criterion means that C cannot be defined entirely in terms of A and B.
Just in this case or overall?
Overall, because it has to meet this fourth condition. This is the kicker.
Saying that. Which is another way of saying that we haven't whittled ourselves down from the TT and FT cases. A and B.
Yeah, well, what this says is, what I did is I defined the cases in which C is true, but there's this fourth case or this fourth condition where we are in this case, but we don't know. C has to be open to being true or false in this case. It actually has to be agnostic about this case. This is the case that it's agnostic about.
And you're saying this fourth is telling us something?
Yeah, and that's what you were getting to. That's why I was like, you're definitely on the right track, because that's what you were getting to in your scratch work there. So So, for example, we might try, let's see, be a try that out and see if it comes out right. So if we do the first condition, A, if and only if B, if A is true, then B is true because A implies B, right? And so then C is true because they're A and B are both true.
Yes.
So it meets the first criterion. Second, C does not imply A. If you say A, if and only if B, A might be false. And then
B could be true, which would then...
Well, B would have to be true. Oh, no, if A is false...
B could be either true or false.
That's right.
And so then our overall material equivalence is false.
But it could be false. A could be false and B could be false. And then the truth of C doesn't imply the truth of A. So it meets the second criterion. Then now let's go to the third criterion. Assume C is true again.
Oh, we're supposed to invent a sentence? Actually invent a sentence.
That's the most natural way of doing it, is actually giving us one.
Oh,
if you could do it more generally, that would be awesome.
What I thought we were supposed to do was whittle the cases down to show a global.
That would be
we did in 19.
It would be great to articulate that. Yes, but really, to solve the problem, all you need is just a statement that fits all the criteria. Right? That's what it says. It says there exists a statement. If you show me a statement that fits the bill, you're done. And that's typically it
says there exists a sentence triangle. Exists a sentence square. So when I see stuff like that, like beach ball, when I'm in Algebra 1, I take it to mean in the general sense of square, not go invent me because it says there is a sentence square. It doesn't say go show me a statement of. There's no way you can get to know that that's what you owe as a deliverable from there is a sentence square.
So maybe this is the natural inclination of people who have done logic for a long time.
100 level course.
So and when we get to quantification,
for beginners, it says.
Right. This is a book for beginners, right?
Well, okay. If you want a statement, you got to.
But this is not like you're being tested, right? You're not being tested. You're going through an experience. This is an experiential.
It's certainly an experience.
Yes. So Jeffrey's not preparing you for everything in the world. Now, if C is true, then we know B is true.
Which one are we on? Which
third conditions? Assume C is true.
Yeah.
Right. So A, if and only if B, we know that when C is true, we're either in the TT case or the FT case.
So, and we get to pick, but we have to allow for either case. So in the FT case, we don't meet the criteria.
We do. So let's see.
Oh, because we're going to be false in that case. C would be false.
So B is true in either of these cases.
Right.
So that's what we showed up here. So A, if and only if B fits the bill.
Oh, so then you have to test A true and test A false and see if things work out.
Yeah. I mean, whenever, so it could be that they're false. Actually, it could be that they're false. So C is true.
But it's not in the realm of
Oh, so this is actually where this example breaks down.
Okay.
So this doesn't meet the third criterion.
Because it could be FT.
It could be FF.
Wait, but it's not, how come it can be FF?
Well, just thinking, starting with C. So let's assume C is true, A if and only if B. That's true when A and B are false.
When can that be a good
when is that true? Yeah. But we need it to eliminate the FF case, and it doesn't. This particular C does not eliminate the FF case when C is true. See what I'm saying?
Oh, and we already said it needed to do that.
Right.
But this particular example didn't do it.
This doesn't do it. But it does, I think it does meet the fourth criterion. If we assume B is true, then A could be true or false, right? Right. If we assume B is true, then we're in one of these cases. In both cases, or in one case, A is true, and in the other case, A is false. And so we don't know if C is true, therefore B does not imply C. So this works in this fits three of the criteria. It just doesn't fit the third one.
Is the thought process was, if you can come up with an actual logical statement, then you've demonstrated that, yeah, there is at least one square. Here it is.
That's it. That's all the proposition is saying. There is a sentence.
But there may just be one very unique example. And so if you don't derive to it, you won't get it. Versus just kind of throwing out, oh, let's try.
Right. So when we hear there exists, that means there's at least one. And usually with theorems that are stated this way, there's usually like an infinite number.
Yeah. You always add or to the end, but those are kind of trivial.
So like in mathematics, when you have a proposition that says there exists,
unless it's zero,
it means there's at least one.
Yeah.
But it usually means there's an infinite number.
Yeah. Unless they're like 0, 1, or infinity. Those are like the examples where you have like a single answer.
Right.
You know, so you check those ones, and if it's not those, then there's a bunch.
Yeah.
All righty.
Okay. So that should help you a lot.
I have things to try anyway.
And this trial and error is not so bad. You start to understand the trial and error actually teaches you a lot.
The machinery under the hood.
Mm-hmm.
Yeah.
Yeah. So don't be afraid to just do a little bit of trial and error and then see if you can
I'm not afraid.
capture the essence.
There's just only 24 hours in the day. So
yeah.
You can only spend so much time on it.
But I think I think we've cleared up a lot today.
Yeah. I'll have to work on my argument for the definition of validity.
Yeah, just think it through. And I recorded this, so I mean, you may want to watch this through again.
I'm pretty sure it's incomplete still. But
it's the official definition.
I know. That's why I have to be ready to argue it if I'm going to argue against all of since medieval time.
It's like a scientific, concept, like a quark. Once a quark is defined, you can't change the definition. If you find something that seems quarkish, but doesn't meet the definition, then you have to define another object.
The lights will be turned off when I move the switches to the down position. There are no switches in the room. Therefore, the lights are off. No,
No,
they're on.
they're on, yeah.
Right,
Because you
Exactly.
didn't move the switches, because there are no switches.
right. So and yet they're vacuously on. See?
Or really on. Maybe they're just permanently on.